think you all got me your homework, yes? You emailed it. I
Yes.
took yours. You gave it to me last time. You already emailed it to me. So cool. Oh, there he is. I'm gonna shut the door. I was just wondering. I was looking to check my email to see if you had emailed or not. Then I'll walk you out.
Of course.
Appreciate it.
Just
Running a minute late.
You already stabbed me today. I feel like it was an accident. You almost amputated my finger. It was an accident. We walked too close in our hands.
They say the first time.
All right. Any questions about anything?
Wonderful.
Is it really?
Also, I talked about it last time and then didn't hand it in, so I'm just gonna hand it both in right now.
Okay. All right. No questions? Things are okay?
Are my name?
I'll figure out who it
I
is.
mean, there's only 6 of us.
Yeah, there's
Process of elimination.
Yeah.
You know?
2 of you emailed it.
Yeah.
Masana's is always in blue ink. So,
Yeah.
so. All right. Well, let's continue then our discussion of modular arithmetic stuff. So last time we talked about the fact that congruence modulo a number is an equivalence relation, and then started discussing equivalence classes a little bit. We've already talked, honestly, we've already talked a little bit about equivalence classes in some respect when we're talking about ways that we could write different numbers. Say if it was like if it was a multiple of 3 or 1 more than a multiple of 3 or 2 more than a multiple of 3. That really is just another way kind of to describe equivalence classes. So as an example, how can you always write an odd number? Or an odd or an even number? An odd number you can always write it as, like a 2k plus 1, or an even number, 2k, good. Notice that what you're really doing is describing equivalence classes modulo 2, right? Odd numbers, you'd have, you're looking at things that have remainder 1 when you divide them by 2. So modulo 2, that would be the equivalence class of 1, right? And then even numbers would have no remainder, so you could think of that as the equivalence class of 0. And notice that everything is in one or exactly one of these equivalence classes, right? Either number is even, an integer is even or it's odd. So it either has remainder 0, makes it even, or remainder 1, makes it odd. You could also pick other elements, of course, that generate these equivalence classes, right? I wrote the equivalence class generated by 0, or equivalence class of 0, equivalence class of 1, to denote these two classes. But you could have also said, well, the evens are the equivalence class of 8, or the equivalence class of negative 16, right? There's nothing necessarily special about 0. Likewise, for the equivalence class of the odds, you could use 5, or you could use negative 19. You could use any odd that you would like. One of the reasons why we typically use 0 or 1 in this case is because those are your possible remainders when you divide by 2. And use those kind of as our, some number theory books call those residues. So we're using the remainders as the equivalence class representative, and that's what we'll typically do when we talk about equivalence classes modulo a number. We'll typically use the remainder to denote the representative of that particular class. Not unlike when you do fractions. Usually when you have a fraction, you reduce it to lowest terms. That again is taking out a specific representative for that equivalence class, all the things that are equivalent to, say, 1/2, for example. But you could also represent 1/2 by 4/8 if you wanted to, and sometimes it's nice to be able to do that. Okay. So anyway, you've already talked about equivalence classes modulo a number kind of implicitly. one of the problems we did back in the previous chapter, I think, said we started with something and said we wanted to write it was of the form 3k or 3k plus 1, but not 3k plus 2 or something along those lines. I think we had one like that. So, in any event, that's the same kind of idea. All right. So, one thing that I want to notice with these equivalence classes, let's do a specific one. Let's say we wanted to write down the equivalence classes modulo 5 to start with. Something that's more than just a couple, but not, 20 of them. So, how many distinct equivalence classes would we get? Well, we're doing modulo 5. There's 5 possible remainders, so we should have 5 equivalence classes, right? Okay. So, we should have an equivalence class for each of the remainders. So in the first one, we would have everything that's equivalent to 0. The things that are equivalent to 0 are the things that have remainder 0 when you divide it by 5. What do you get when you get the equivalence class of 1? What kind of things are we looking for there?
11.
Yeah, so the positive ones would be 6, 11, 16. The negative ones would be... careful.
Wait. Oh, yeah, you're right. Would it be -1? No? -4?
-4, -9, -14, and so on.
Ooh. That's disgusting.
It's not disgusting. Remember that the definition is that you have to divide the difference of the two, right? If I do 1 minus a -4, I get 5, which is divisible by 5. If I do 11 minus a -14, I get 25, which is divisible by 5. All right. So what do you get for the equivalence class of 2?
-13, -8, -3, 2, 7, 12.
Yep. Good.
The negatives are the confusing ones. That
Yes,
just so
they
backwards.
are backward. They're not disgusting. The way I typically do it is I'll just do the positives first, and then to get the negatives, I'll subtract. I'll subtract a 5 in this case, and then I can just go from there to subtract or add 5 each time. And think about why you can do that. You're just writing the numbers as 5k or 5k plus 1, or 5k plus 2, 5k plus 3, 5k plus 4. The k could be negative. This makes it a little bit easier. At least in my mind, it makes it a little bit easier. So for the 3s, you'd have 3, 8, 13, 18 for the positives. Mm-hmm. Oh, yeah, and you can also just add 1 from the previous spot, too. We're just going up by 1 each time. But if I think about going backward now, this would be -2, -7, -12. And then we can fill in the 1 for 4. Pardon me. But notice again, these really do follow the same rules that we proved for general equivalence relations. Remember, for general equivalence relations, I didn't take your cord, did I?
No.
Okay.
I'm just trying to move this so you don't.
Well, hopefully I won't roll back any farther. I might get really excited though and push myself completely across the room. If I did that, I'd probably fly over backward. And if I'm going to do that, you might want to have a camera up, right? Make sure we can upload that to TikTok. All right. Notice that the equivalence relations, try that again. The equivalence classes here are disjoint, right? There are no overlaps, which is what we could prove for general equivalence relations, right? Equivalence classes do not have any overlap at all, okay? and every integer is in exactly one of these equivalence classes. Their union is all the set of all integers. Right? Okay. So the equivalence classes here really do partition the integers. Now, what we're going to want to do in the next section that's leading up to our kind of first abstraction for structures is that we're going to want to be able to define an operation on these equivalence classes rather than on specific integers. Now, that sounds relatively scary, but you've done this before back in grade school, not necessarily with integers. You do this when you add and subtract fractions, right? So what I mean by that is if you want to take the fraction 1/2 and add the fraction 1/3, what do you do the very first thing? Get a common denominator, right? So what you're doing is you're finding another element in the equivalence class of 1/2 and another element in the equivalence class of 1/3 so that they're compatible to be able to do the operation, right? So the first thing you do is, okay, I'm going to take out this operation and make this take out this representative and make it 3/6 instead. Take out this one and make it 2/6 instead. Oops. And get 5/6 when we're done, right? That's what we do. But again, there was nothing necessarily special about 6 except the fact that we get the same denominator. We could have used 12, for example, right? You could have done 6/12 and 4/12 to get 10/12, right? Notice I ended up in the same spot. Okay. So the important part is that if I want to do the operation, it needs to be independent of the representative that I pick. Okay? If I pick a different representative, I don't want to get a different answer. I need to get the same answer or an equivalent answer in this case, right? These aren't the same answer. 5/6 and 10/12 aren't the same answer, but they are equivalent answers, right? Okay. So anytime we do operations on equivalence classes, it needs to be what we say is independent of the equivalence class representative. Okay. So what I mean by that is if you want to define the equivalent class of 2 plus the equivalence class of 4, that needs to be exactly the same thing as the equivalence class of -8 plus the equivalence class of 24, for example. Those need to be the same. Okay. If it's going to be well defined. If it matters how you pick the representative for the answer, then this addition is not going to be well defined. Does that make sense? So notice, how would you like these to be defined, by the way? What would you like to do with these representatives? What did we do with the fractions? Well, if I wanted to add the fractions, I just added the representatives, right? I just got compatible representatives to do it, right? It was just representatives. So I really want this to be just add the representatives together. That's the easiest way to do it, right? Over here, you would have 16. Are those two equivalence classes the same? Is the equivalence class of 6 the same as the equivalence class of 16? Yeah, they're in the same equivalence class, right? Here's 6, here's 16. So that's okay. That's what we want, right? These two things really are equal to each other.
Wait, how are they in the same equivalence class?
They're both in the equivalence class of 1.
Oh, okay.
Yeah. Yeah. That makes it, yeah. Is that okay? Yeah.
We did this yesterday in computer architecture, and he was like, well, you guys haven't got there. So we got there yesterday.
That's really funny. Now, we have the equivalence class of 6. We have the equivalence class of 16. Those are both the same, but those might not be the one that you want to refer to all the time. Much like over here, I have an answer of 5/6 here and an answer of 10/12 here. When you do fractions, typically you reduce them, right? Back in grade school, one of the things you get it at lowest term, right? All the time. Okay? So we're going to do the same kind of thing here. I have this kind of basic set of equivalence classes over here, right? I've got these 5 that we generated. Can I take one of those, that 6 or that 16, and make it one of those other 5? Which one should I use? So if I want to use one of the ones that on the left-hand side there, that I've got the specific ones that I represented, which one do I want to use? The 1, yeah. That's the kind of, I've got the kind of those 5 basic ones, right? Those are the remainders modulo 5, right? So I probably want to use this and say the answer is 1 here. Notice how you could get there. Well, I can reduce 6 to 1 by just modding out by 5, right? Mod out by 5 and get the remainder. Pardon me. So this is exactly what we're going to do in the next section. But to get there, we need a theorem that helps us understand why this actually is true. And this is theorem 2.2. And it says that if A is equivalent to B mod n and C is equivalent to D mod n. And I know the book puts the parentheses around there, and I'll try to remember to do that, but I probably won't put parentheses around the mod part all the time. The first part says that if I add A and C together, I should get the same thing as when I add B and D together, mod n. And if I multiply A and C together, I should get the same thing as if I multiply B and D together, mod n. So again, if we think, trying to fall over. If we think about this in terms of equivalence class representatives, this A and B, if they're equivalent, that means they're in the same equivalence class, right? Same thing here, C and D, if they're in the same equivalence class. So if I take A and C and add them together with these 2 representatives, I should get the same thing as when I add them together with these 2 representatives. That's what the first thing says, right? I should get the exact same equivalence class, which is what we were talking about here, right? If I take the 2 and the 4 and add them together, I get the 6. I take the negative 8 and 24 and add them together, I get 16, but I really do get the exact same class, modulo 5. Right? So that's all this theorem is saying. It's just writing it in terms of the modulo relation. So let's see if we can prove this. Why am I dropping this thing today? Okay. So if we want to prove it, remember we're starting with A is equivalent to B mod n, and C is equivalent to D mod n. I would first convert the modulo statements to division statements. With the definition of modulo, A is equivalent to B mod n means the same thing in terms of division. What? What do we say? What divides what?
N divides A minus B.
Yeah, good. If then n divides A minus B and n divides C minus D. Oops. Now if we go to definition of divides, how do we rewrite divides by definition? Good, okay. So there exists, I'll call it K and M, okay, such that NK is A minus B. What is going on? There we go. I don't know why I wasn't writing. A minus B and NM erase. Good grief. C minus D. So all we've done in these first couple of sentences is just rewrite what the definitions are, right? The definition of being equivalent or congruent modulo n is that n divides their difference. And then the definition of divides is that it's really n times something gives me the a minus b, right? Okay. What are we trying to get to? What are we trying to prove for the first part? I always tell people I'm a mathematician. I can handle awkward silence. I consider it all day. What are we trying to? What is for number one telling us to prove? What are we trying to figure out? You can just literally restate the statement to me, and then I'll ask another question. There we go. Okay, just okay. They're trying to show that a plus c is congruent to b plus d. What does that mean? I need to show.
Oh, can you just add those two equations?
Okay, yeah. So I want if I just think about what this statement says again, how can I restate this? You're right. This is exactly what I want to do. But how can I restate this statement?
N divides A plus C minus B plus D.
Right. Good. I want to show that a divides a plus c minus b plus d. Right. So if I want to see an a plus c and a b plus d, like Masana said, what do I probably want to do with these two equations? Add them. Yeah. So now, if we add nk and nm, what do we get?
It's equal to
A minus B plus C minus D.
Okay. And then we can rearrange to get what? N times k plus m is equal to what?
A plus C minus in parentheses B plus D.
Good. And isn't that what we wanted to show, essentially?
Mhm.
So just a conclusion statement here. Hence, n divides a plus c minus b plus d, and they're congruent. Oops. A plus c is congruent to b plus d modulo n. So again, the idea behind the reason why we would care is for what we're showing here is that the equivalence class representative doesn't matter if we want to try to define an addition operation on the equivalence classes. Okay. I know a lot of you haven't had advanced computer programming. In computer programming, there is an operation that's referred to as operator overloading, which means that you use the same operator to define a similar operation, but for a new structure. So for example, when you're programming, you might add integers, and that plus sign means take the integer plus the integer. But it might also mean that if you have a real number and a real number and add them together, that plus sign means add the reals, right? Don't just add the integers, but add the reals. Or if you have one string and another string, that plus sign might mean put the two strings together, right? But you're using the exact same symbol, but it means different things depending on what structure you're pulling it from, okay? That's what we're saying here. This plus sign, we're used to the plus sign meaning add integers or add numbers, generally speaking, right? Now we're going to use the plus sign to mean add equivalence classes. The thing that allows us to do that is the fact that it doesn't matter which representatives I pick, I get the same answer. The second part of this just says that we can also do that for multiplication. You also did this a little bit in linear algebra, right? We talked about adding vectors together. When you add vectors, that's different than adding numbers. Also talked about adding polynomials. That's different than adding numbers, but you're using the exact same symbol, right? Basically, we're overloading the operator.
We actually touched on that in the intro course for programming.
No, did it?
Everybody
Okay.
took the first course of CS when we did object-based
Oh, yeah.
programming. One of the things he showed was overloading the operators within that object class
Yeah.
to make it work a different way in the object class.
Yeah, exactly. Yep. So same kind of idea. We're just overloading what plus means, defining it on a different object. It's amazing how that stuff's all related. All right. So we proved it for addition. Do you think you could also do the same thing for multiplication? Probably. Okay. So we have to be a little bit more clever with the multiplication, but it's not too bad. All right. So we needed, like we did here, we needed to show that n divided the difference of the sums, right? We need now to show that n divides the difference of the products. So let's start with the difference of the products. Pardon me. We want to show that AC minus BD is some multiple of n, right? All right. So let's be a little bit, pardon me, clever here. I know that A and B are equivalent mod n, and I know that C and D are equivalent mod n. I don't really have any way to get that together, but let's be clever and let's add in 0 cleverly and see if we can get to what we need. So let's add in BC, kind of like a bridge, if you will, for what we need. Looking at the first two terms, what can you factor out? A C. And looking at the second two terms, what can you factor out? B. And now we already have A minus B written in terms of something. So what can we replace the A minus B with? Okay, good. And for the other one? An M. And so now we can factor out an N out of both terms. So once we get to this point, what does that tell us?
N divides.
That AC minus BD piece? Yeah, good. All right. So from this, we can start talking about making up what I like to call basically arithmetic tables for certain structures. So let's look at an addition and multiplication tables for the integers modulo 6. All right. So just making tables like you would in grade school. Okay, and we're going to fill it out much like what we did in grade school. One of these we refer to as a Cayley table. We'll talk more about what I mean by that later, so you don't have to worry about the particular name. Just think about them as operation tables at this point. Okay. I want an addition and multiplication tables for the integers modulo 6. Well, if I'm doing integers modulo 6, how many distinct equivalence classes do we get? I think there's 6, isn't there? What are your remainders? 0 up to 5. Yeah, you got to count 0 in there as well. So I'm going to use, I'm not going to use the notation the book does because I'm getting tired of putting the brackets around it all the time. I'm lazy. Another notation for equivalence classes is to put a bar over the top. So it's just faster for me to write it that way, and I'm lazy. I'm going to do brackets every single time. And in fact, eventually I'll probably just not put the bar on there either when we understand that we're talking about equivalence classes. Okay. So I'm going to make up multiplication table as well as the addition table. And we're going to fill this out using the properties that we just proved. So if I add, it doesn't matter the representatives I pick, I can pick the smallest representative that I want. So if I add 0, let's just kind of go across. If I add 0 to 0, 1, 2, 3, 4, or 5, what do I end up with? Yeah, I get the exact same thing, right? 1, 0, 1, 2, 3, 4, 5. What happens when we add 1 across? When we do 1 plus the 0 will give me 1. 1 plus the 1 will give me 2. And I keep going. But finally, though, when I do the 1 plus the 5, 1 plus 5 is 6. But in the list from 0 to 5, which is the equivalence class of 6? Or the same thing as the equivalence class of 6? The equivalence class is 0, right? And basically, what I can do is I can just take the 1 plus the 5, I get 6, and then just reduce it modulo 6 and get the 0, right? So what's the next row going to be?
2, 3, 4, 5, 0.
Good. 2 plus 4 gives me 6, but 6 mod 6 is 0. 2 plus 5 is 7, but 7 mod 6 is 1. So I can just use 0 and 1 for those representatives. Does that make sense? Okay. So then, hopefully it's not too bad to fill out the last 3 rows here. Are we okay with how we're filling these out, by the way? Yes, good. Okay. We're going to do the exact same thing to fill out the multiplication table, except that we're going to multiply rather than add. So what's the first row going to be? All zeros, right? Because again, we're going to multiply and then reduce mod 6, but 0 times anything is 0. Mod 6 is still 0. How about your next row?
0, 1, 2, 3, 4, 5.
Good. Next row?
2, 2, 4, 6, 8, 9. Oh wait, no, we can't. Sorry.
Yeah, it's okay. So what's 6 the same thing as? 0 and then 2, 4. Good, yeah. For 3?
2.
Yeah, we're modding 6. Yeah, 0, 3, Good. Yep. And then yep.
042.
Yep. And then the last one. Yep. I agree. Yeah. 5 times 2 is 10. Mod 6 is 4. 5 times 3 is 15. Mod 6 is 3. 5 times 4 is 20. Mod 6 is 2. 5 times 5 is 25. Mod 6 is 1. Oh, that's how that last one gets spelled out. Okay. This okay? All right. So before we go on and do some more definitions, I want to look at the structure here of both of these things. Because one of them, well, it looks kind of weird. So let's look at this one. Notice that when we added 0 to anything, we just got the anything back again, right? So we have an additive identity. You've talked about additive identities before in linear, right? We did that for vector spaces, right? The thing that you add to an element and it doesn't change the element at all, okay? So we have an additive identity here. Notice that for this additive identity here, when we did multiplication by it, we got that additive identity back again, right? We got the 0 times anything here as 0. Okay. So notice that we've got the additive identity here. There's an interesting structure that goes on here. We're going to come back. We did that in linear as well. Remember when we did the 0 times any vector gave us 0? We use properties of vector spaces to prove that. Same idea is going to happen in these structures. What about here? Let's look at this particular element. What is that behaving like? When I do 1 times anything, I get back to what I started. So it's also some type of identity, right? In this case, we have a multiplicative identity. So this particular structure has 2 different types of identities. It has one identity with respect to addition, and it's got one identity with respect to multiplication. Again, in linear, we had kind of that scale factor when we said 1 times any vector was the vector back again. It's the same type of property here. Notice in this structure, we have the additive identity. Everything has a match that gets it back to the additive identity. Back in linear, again, we had the additive inverses, right? This is exactly what we have here. We have every element has an additive inverse. Of course, that one's its own inverse, right? But every single element has an additive inverse in this case. Looking over in my multiplication table, does every element have a multiplicative inverse? Does everything have something I get back to the multiplicative identity? So let's look at this row. Do I have something I multiply by 0 to get to the multiplicative identity? What's the multiplicative identity?
It's just in those ways to get itself.
Right. So I'm looking for something to get back to the multiplicative identity. So in this case, what is the multiplicative identity? What specific element is the multiplicative identity? 1. Is there something I can multiply by 0 and get back to 1? No. Okay, so that one doesn't have a multiplicative inverse, which makes sense, right? We know that we can't undo multiplication by 0, right? So 0 not having a multiplicative inverse is something you're used to. At least I hope you're used to that, okay? Because you already know that you can't divide by 0. The reason why is because you don't get a unique answer. I mean, there's technically nothing wrong with dividing by 0. You just get infinitely many answers. Okay. All right. How about for 1? Is there a multiplicative? Is there something you could multiply by 1 to get back to 1 again? Yeah, just multiply by itself, right? And what about 5? Is there something you can multiply by 5 to get back to 1 again? Yeah, itself again, right? But what about 2, 3, and 4? Is there anything you can multiply by 2, 3, or 4 and get back to 1? No. So these particular elements do not have multiplicative inverses. What that means algebraically, and we're going to investigate this more as we go along, what this means algebraically is that, okay, you're used to solving equations like this in the real numbers, right? What do you do to solve for x? Divide by 2. Can I divide by 2 in this particular structure? No, because I don't know that it doesn't have multiplicative inverse. So in this structure, if I replace these by equivalence classes, this may or may not have a solution. We can't tell to start with because I can't get rid of the 2. Okay. Now in this case, it doesn't have a solution, but it may or may not have a solution. Or it might have many solutions. We just don't know. We can't tell by looking. And again, the reason for this is because, why are you not scrolling? No, of course, I know I'm flying. The reason for this is because we can't, I'm going to put this in the quotes, divide by 2 in this structure. Really, I mean multiply by its inverse. I can't multiply both sides by its inverse, but we think about, usually when we think about solving equations, what we're used to before this class, you think about it as division, right? So it may not have a solution. It might have many solutions. In this case, I can look at my table and see that there is nothing where I take 2 times it and get 5, right? I can just look at the table. Agree? Okay. However, if you wanted to solve, say, 3x equals 0, how many solutions does that equation have? Just look at your row again. Yeah, it's 3 solutions. What can I multiply 3 by and give me 0? I can multiply it by 0, I can multiply it by 2, and I can multiply it by 4, right? So this has 3 solutions in this structure. It may have more or fewer, depending on the structure. Okay. So the reason why we do there's lots of reasons why we do this stuff, but one of the reasons why you study abstract algebra is because you're used to things working out nicely, if you will. And we're just asking what happens if things don't work out nicely. Okay. You're not used to having a linear equation that doesn't have just exactly one solution. Okay. In this case, we've got 3. And we're just trying to investigate what happens when you start talking about these other structures that have similar properties to what the integers have and have similar properties to what the real numbers have. All right. So let's investigate this structure a little bit more. And this is in section 2.2. Oh, we already talked about it a little bit. 2.2 is modular arithmetic. This is the name of the section. Basically, this is going to go into section 2.3 as well. Pardon me. But what we're interested in this section is doing exactly what we were just talking about how we define our operations and then talk about what properties these operations have and what properties these operations don't necessarily have. Okay? So when we define addition, let's start with this. For any integer, Why are you being such a pain today? For any integer n greater than 0, we're going to define the integers modulo n as the notation is your integer symbol, the z, and we do a little subscript n. This is the set of all equivalence classes, distinct equivalence classes, modulo n. Just to denote that I'm talking about the same n here, I'm going to put a little subscript here to denote that we're modding out by the n. I'm not going to write that all the time. I'm just trying to illustrate that the equivalence class that we have is generated by the fact that we're modding out by that specific n. For different n's, we'll have different equivalence classes. Okay? All right. So we usually say z mod n or just zn here. But we just mean take the integers, mod out by n, and look at the equivalence classes that we're left with. So in particular, if I want to know what the size of this set is, well, you've already told me that if I mod out by n, there are n possible remainders, so there are n equivalence classes, right? So every one of these is just going to have size n. Be n elements in that set. So even though, of course, I've got infinitely many elements in Z, I have infinitely many integers to do, I only generate finitely many equivalence classes because there's only finitely many remainders we have. Okay. This is what we mean by Z mod n, and then we define addition by just adding the representatives, and we define multiplication by multiplying the representatives. This is how we're going to define our addition and multiplication modulo n. Take your representatives, take a representative from each equivalence class, add them together, look at the equivalence class generated by that answer. And then the same for multiplication. The reason why this works, the reason why this is well defined is because of what we proved by that theorem 2.2. Doesn't matter if I take different representatives from the same equivalence class and do these operations, I generate the same answer. The representative might look different, but the answer, the equivalence class that it generates is the same. We proved that in theorem 2.2. Which is exactly how we filled out those tables, right? We said that, for example, when we did 3 times 4, 3 times 4 is 12, but 12 generates the same equivalence class as 0, so I might as well just call it 0. That's all this is saying down here. All right. So this is modular arithmetic. That's what we mean by modular arithmetic. We have defined how we add and how we multiply. That's it. Okay. When you say arithmetic, though, you think of what you've learned in grade school. What kind of properties does arithmetic have, right? So this is where the abstract part comes from. We're going to look at, well, what properties of arithmetic do we care about? And then see what properties of arithmetic these particular structures satisfy. So what's important? Okay. Well, let's think about what's important when you solve an equation, and then see if we can generate what properties we might want. Okay. So what I mean by that is, if you wanted to solve, let's just do this particular linear equation. If you wanted to solve this equation, 3x minus 4 equals 2. Back pre-algebra, right? Ignore everything we've learned so far in this class. Just go back to learning how you solve these equations. But let's honestly look, and I think I've talked about this in linear as well. Let's honestly think about everything that you need to know in order to solve this equation. Okay? Again, our goal to solve this equation is to do what? Yeah, find x, right? Get x by itself, correct? Okay? So what do we need to do first to get x by itself? I got to add 4, right? I have to be able to undo minus 4, right? In order to be able to undo minus 4, I have to know that there is an additive inverse idea, right? Okay. The reason why we want to make sure that we have an additive inverse is the fact that I need to get that 4 to go away and make a plus 0, correct? So the first thing you need to make sure that we can actually do is be able to add that 4, right? So I need to make sure that additive inverses exist, right? Agree with that? Okay. Now, why did you add 4? What do you want it to happen on the left-hand side? What's the point of adding the 4? Yeah, cancel out the minus 4 and becomes 0, right? It makes it 0, correct? So, but before I can cancel those, notice that I'm really adding 4 to the number I'm calling 3x minus 4, right? That's in parentheses, is why I put it there. Okay. In order to add the 4 to the negative 4, what do I need to do with the parentheses? Move them, right? So to be able to actually cancel those things, I need to know that I can do this, right? Agreed? Okay. What property do we call that when we regroup? It's the other one. It's associative, yeah. Yeah, commutative means we flip them around. Yeah.
Oh, that was fast. I was still grasping for 1. That's one I know.
That's one you know, yeah. That's associativity. Good. So we need to know associativity. When we write it as 0, I'm going to just make the 2 plus 4 6 so I don't keep writing it every single time. The reason why you told me that we added the 4 was so that it canceled out the negative 4 and made a 0, right? Why did I want a 0? What does the left-hand side become? Just 3x, right? That's an additive identity, so I need to make sure I have that too, right? Agreed? Okay. So notice that just being able to solve these things, I've got 3 very, very important properties that have to happen, right? I need that additive identity, and then I get to 3x equals 6 at this point. Okay? All right. So these are important additive properties. Now, of course, your next step would be to divide by 3 or multiply by its inverse. What we've already seen, though, is that for modular arithmetic, we don't always get inverses, right? So we may or may not be able to divide by 3, depending on what the structure is. Agreed? However, if we can divide by 3, let's assume that we're in a structure where we can divide by 3. Again, I need another property, don't I? To be able to get the 1/3 and the 3 to cancel. We need associativity again for multiplication. Oops. When the 1, 3, and the 1/3 and the 3 cancel each other out, we get a 1. And then again, just like we did for additive identity, I need a multiplicative identity. So this one is iffy. We'll talk about why that one's iffy to start with. I don't always know that multiplicative inverses exist, right? But if they do, again, we need another associativity property. And this is for multiplication in this case. And then we also need a multiplicative identity property. This is why Algebra is hard for kids. Look how much stuff goes into just solving that equation that we don't even think about it anymore. But if you're just thinking about going back and learning it for the first time, there's a lot of stuff in there. Right? A lot of things you have to keep track of. A lot of things that you have to understand why we're doing it. Okay. All right. In any event, the idea here is which of these properties do we consider important? Which of these properties do we want to investigate when it happens? Okay. Important ones are what? Well, having an additive identity is important. Being associative, having additive inverses, all those addition things that you're used to having are important ones. So these are kind of your arithmetic axioms, but we're going to just state them in terms of modular arithmetic. This is theorem 2.7. We'll let A, B, and C be in Zn. And now, of course, I'm using brackets again, but I swore I was going to switch over to bars. Okay. These axioms are going to look a lot like your vector space axioms. They're going to be a little bit different, but there are the same number. There are 10 of them again. But they're things we're already used to. Okay. First one just says that if I add two things in Zn, I'm back in Zn again. What axiom did we call that back in linear? If you add two things from your structure and you get back into your structure again, we called that? What was it?
Closed under addition?
Yeah, it's get closed. Exactly. It's closure. You're good. This is closure under addition. Good. This is a side note that doesn't have anything to do with this class, but closed means something different in analysis. Math people like to use the same word to mean different things. Yay.
I mean, that's what we're talking about today. This isn't addition.
What's that? This isn't addition. Yeah, it's something else. It's operator overload.
We're talking.
Or just mental overload. All right. The next two are ones that you're used to. One we mentioned a minute ago. I hate drawing these brackets every single time. Are you okay with I switch over to the bars over the top?
Yes. I would too as well.
I switched midstream. I got to put it right in the brackets.
Hate it when that happens.
Switch midstream. All right. So, what property did we call that?
Associative.
Associative. Yep, good. This is associativity. Under addition. For those of you going on to teaching, make sure you don't abbreviate associative inappropriately.
Kids will do it for you.
I'm sure they will. Actually, there is a notation in commutative ring theory that talks. It's so for the set of associated prime ideals. Sounds scarier than it is. The abbreviation is AS of R. I'm dead serious. I've written papers where I've referenced AS of R. Those are my favorite papers.
Write an apology letter to R.
What's that? What'd you say?
So write an apology letter to
The
R.
R, yeah. All right. The third one says that.
Brackets.
Oh, I'm going to switch back to my brackets again. Ah! Sorry. I told you I wasn't going to do that. Jump scare. See, and then my problem with the bars over the top is because I'm so used to teaching classes with vectors in it, and then I make a little arrow over the top, which I don't want.
I hate writing those little arrows.
I do too.
I don't know why it bothers me so much.
Why do you think I only do a half arrow?
Yeah.
Yeah, I can't. I don't want to put the other top in it. No, my arrow is always lopsided. I'm not picking up the pencil to go to the other side. It's not going to happen. Property we call this one? Commutative. Good. I could also write that as a plus 0, but in this one, we're talking about what property are we talking about here? Oh, it does equal a. Thanks. There. How's that? Better?
Yeah.
What property do we call that? Sorry. Identity. Good. What is this? What does that say? We have additive inverse is good. All right. Before I write down the next 5, I do want to take a little side note because this is stuff that we're going to talk about later in the semester. So I'll start trying to keep things compartmentalized. Ignore 3 for the time being. Okay. Ignore 3 for the time being. 1, 2, 4, and 5, and in particular, 2, 4, and 5, associativity, having identity, and having inverses, that creates what we call a group. Okay. We have one operation that we can reassociate. We know that there's an identity and we can undo it. That's what we call a group. The reason why we don't put commutativity in that is because, again, if I think about just trying to solve this equation, I don't have to reorder anything. Right? Okay. I can do this and then go on down the line, right? I didn't have to reorder anything. So commutativity is not in the group axioms to start with. Okay. And when you put commutativity in there, we refer to that as an abelian group. Abelian name for Niels oval, I believe. I think I mentioned that the other day.
Spell that.
Abelian, Abelian.
Acceptable.
Yeah. Okay.
Formally requested name change.
Anyway, so these would be the axioms for commutative groups, abelian groups. So we'll come back to groups later in the semester, but that's what those axioms are. All right, so next.
And back
Doesn't it feel like linear algebra a lot?
back to back.
Oh, shoot. I didn't put it back right. I was just looking at the book. Sorry. How's that better?
Without brackets, no. It looks a little weird. I have to put mine in parentheses.
All right. What's that again? For just saying that if I multiply them together, I get back in there again. This is another closure. Yep, this is a closure under multiplication. All right, you've seen this one before. Oops, sorry, you've seen the next several before. This one is associativity again. I'm being lazy with my abbreviations. And see, I told you I was going to write a vector symbol. I could put the bar over the whole thing, but I'll just leave it like that. It's going to both the same one. Okay. What is that property called? That's distributive, right? Now, we haven't done this yet. And the structures we're talking about right now, it won't matter. But remember from linear algebra when we did matrix properties, there was a different distributive property from the left and as opposed to the right, right? Because the multiplication wasn't commutative necessarily. Okay. So to emphasize that, we're going to put the other distributive property in this one. And before I write down the next two, I'm going to mention this. we've defined now a second operation that satisfies associativity and says that the two operations behave nicely with each other. Okay. At this point now, we have, and this also includes number 3, by the way. When you do the first 8 axioms now, we now have what are called the ring axioms. And we're actually going to talk about rings before we talk about groups, which is weird to me because parts of rings are groups, but it's the way this book laid it out. I'm going to give it a shot this time. I've never taught it this way before. So, but you know, after doing this for 26 years, you look for new things to try. So we'll try something new. All right. So anyway, when we stop here, this is the ring axioms. We're going to have 2 more axioms or 2 more things that'll apply specifically to this type of arithmetic. But right now, we're just at the rings. So again, 1, 2, 4, and 5 make a group. Okay. Add in 3, you get an abelian group. Add in 6, 7, and 8, you get a ring. Okay. So rings require 2 operations, an addition and a multiplication. Okay. All right. The last 2 axioms we have are specific to the certain types of rings that we're talking about. This is commutativity of multiplication. AB equals BA. So now at this point we have what's referred to as a commutative ring. So anytime you hear the word commutative ring, it's specifically telling you that the multiplication is commutative. For every single ring, commutative or not, the addition is always commutative. For a ring, an addition is always commutative. The multiplication may not be. Think matrices. Okay? Matrices you can add in either order, but you can't necessarily multiply in either order. Okay? So think matrices when you think about non-commutative ring. Okay. 10 says we have is the multiplicative identity. Again, not every ring has an identity. So if you satisfy this property, you say you have a ring with identity or a ring with unity. It's also another way to say a ring with identity, call it a unity. Okay. Why is that last one important? Think about your even integers. Do the even integers, is there an even integer that acts like the multiplicative identity? No, because you have to multiply by 1, right? And 1's not even. However, every other axiom is satisfied. Okay, so that's an example of a ring without identity. Okay. So this last one also pops up later on for rings, but we know that in the modular arithmetic ones, they satisfy all of these things. Okay. All right. So what we're interested in then is trying to figure out what these structures are. To help us with that, let's look at something like number 13 on page 37. This is a true-false question. And I'm going to write it without brackets. Try this again. AC, not BC. I can write what I'm trying to write. Holy cow. No matter what I pick for A, B, and C, for any Zn, is this true? No. Okay. Tell me specifically what you could use for A and make it not true no matter what the Zn is. There's something very specific that I could use for A and make it not true. I could use 0, right? So So for this argument, let's assume that A is not 0. Okay. 0 certainly would make it false, right? But let's say we had, I said A is not 0. Does that make it any more true for any Zn that we have? No. So, for example, if I do 3, say in Z6, if we do 3 times 2, and I do 3 times 4, what do I get in both cases? 0, right? Those are certainly 0. And certainly 2 is not the same as 4. So this is false in general. The problem is that we don't know that we can divide by 3, right? In Z6. If A always had a multiplicative inverse, then would it be true? If I knew that I had a multiplicative inverse for A, would it be true? Yeah, because I could just divide by the A, multiply both sides by its inverse, right? It would be true if A were always invertible, or always had an inverse. If it has an inverse, we say the element is invertible, or is a unit. We've talked about units before. We'll do more definitions as we go through. But in general, if I know that A is invertible, then I know this is true. But in general, it's not true. So one of the things that we're going to talk about in the next section is, well, how do I know when it's invertible or not? How do I know if something is invertible? Because that invertibility allows me to solve equations. Okay, so that's one of the things we're going to be interested in. So that's what we're going to talk about in the next section. I do want to give you some problems to think about out of here. Let's look at this is going to be some of these will be practice. Some of them I want you to turn in. So practice. Let's look at number 5 on page, and let's see, and 12 on page 31, and this is 9, 12, and 15 on page 37. And then for turning in, I want you to look at, what did you say, 5 and 12? I want you to do 15, 20, and 21 on page 31 and on to 32. Nothing for the other sections, just those 3. For this one, though, for number 21 here, I want you to think about this and also think about, can you devise or can you prove, if you already know what this is, I don't mean devise, I mean prove. Can you devise a divisibility test for 9? And what I mean by that is, using the result that you have in 21, can you find a way to determine if the number is divisible by 9? And if you already know what it is, then use that result to explain why it works. Does that make sense, what I'm trying to say? Okay. All right. Have a good one. We'll see you on Tuesday. We'll finish up chapter 2 on Tuesday and then start to get into chapter 3. And the reason why I've been talking about rings today is because that's what we're going to start on Tuesday, is talking in earnest about different types of rings. And not just the bling bling rings.